Alright, next question. Oh, I hate moments. They're just awfully easy and so boring. Like, come on, bro. A uniform rod, AB, has length 3 meters and weight W newtons. Okay, this is just a uniform rod. We know that its center of mass lies straight down the center. That is going to be W newtons. 3 meters, this is 1.5 meters, this is 1.5 meters. Just label the necessities, okay? Now, the rod is suspended by 2 light vertical ropes. We have tensions in the 2 ropes. Also, just one thing, I just want to check the concept. And that is, this we're labeling as tension, right? Now, this tension doesn't directly act on the rod. The tension is just for the string. This is the force that is acting through the string, inside the string. This is not what's acting on the rod itself or any other object that it is attached to. What is happening though is, notice how the string and the rod is in contact. Okay, they're in contact. That would mean that there's a contact force between them. Okay, and that contact force is what we're concerned of, and that contact force, the reaction force, just happens to be equal to the tension in the string. Okay, well, why, you may ask? Well, okay, let's say the contact force that is exerted on the string. Okay, of course, like here the strings are maybe perhaps attached to a ceiling over here, or else how are they just levitating, right? So there's like a ceiling over here, and the ceiling is giving it, or it's just, you know, it's just, the whole thing is just being suspended from the ceiling. That's what's happening. Now here, if you notice, they're in contact. That would mean there's reaction force, and that reaction force exerted on the beam is going to be in the upwards direction. That is what's keeping the beam levitated upwards. That is how the beam is hanging. You know what I mean? That is a reaction force exerted by the string. Okay, the string is, like, let's say, tied around here, and you have an overall force upwards, and that is the reaction force. And due to Newton's third law, what the beam is going to do is the beam is going to exert the same reaction force on the string, and that's just also going to be equal to R, but this time just in the opposite direction. We know that's just the law, okay? That's what's going to happen. If I push you, I'm going to be pushed back a little. Also, depending on how heavy you are, right? So if you're a nickel avocado, then, well, I'm just gone. If I try to push you, I'll not be seen anymore. I'll not be making videos anymore, and you guys are going to be cooked. Okay, sorry about that. We have these reaction forces acting, so we just figured out that there's a reaction force exerted on the string. Now, we can actually see that if a reaction force is being exerted on the string, that would mean that there's some force trying to pull the string down, right? And that is the reaction force here. And that's exactly what that is. And what the ceiling is going to do is, since the ceiling is also in contact with the string, the ceiling is going to try to pull the string up with another reaction force. Let's call that R. And this will also be R because, well, these two forces actually have to be equal, right? Because we know that the whole thing is in equilibrium. The resultant force in all directions is just going to be 0 for all the objects here, the strings, the beams, whatever. Okay? So that is going to be R, and we're actually pulling the string from 2 different sides of the string. And that is what causes a tension in the string, right? And all of these, the reaction forces that we just labeled, all these reaction forces just happen to be equal to the tension that is running throughout the string. Which is why we just we're just concerned about the tension here. We don't really talk about the reaction forces here. We just do it. It's just the convention. But I just thought you should know that. I just yapped a lot. Sorry. Really sorry about that. Okay. let's just get right into it. Yeah, we know this, blah blah blah. AC is 2.1, good to know. The rod is in equilibrium in a horizontal, okay, blah blah blah. The tension in the rope at C is 350. Now this is what we're interested in. The tension here is 350 newtons. Okay, let's not call both of these tensions just T. They're not the same, of course. I mean, they could be, we don't know, but since we don't know, we shouldn't assume here. T1 is going to be that, and let's say T. Okay, you know what? Why T1 and T2 when you can literally just label them as TA and TC? That would just be better, right? Okay, now we know TC is that. Show that W is 490. This is actually very easy. No, I take that back. Wait, what? Yeah, I guess we have to take moments about A now. Yeah, that's what we have to do. Let's take moments about A, because we're not actually concerned about TA. Well, you know what I thought? Well, I thought that we could actually resolve this vertically, like this. And then we could say that since it's not moving in the vertical direction, resultant force is 0, that would mean that TA plus TC would be equal to W, right? Well, then here, we only know TC, we don't know TA and W, we don't know all of these. So we actually can't solve that equation straight up. So taking moments would actually be better. So if we take moments, we can actually just exclude the tension at A, right? Only if you consider A to be the pivot. So moments about A, what do we have? We have a force that is trying to turn the beam about A in the clockwise direction, that is W. So for that, there's going to be W multiplied, so the force multiplied by the distance from the pivot, the perpendicular distance from the pivot, which is this right here, and we know that this is 1.5. All right, so W times 1.5. Am I recording? Yes, I am. W times 1.5. Oh shit. Okay, W times 1.5. This should be equal to the total anti-clockwise moment. Right? We're just using the basic principle of moments. The anti-clockwise moment is 350. Whoops. 350 times, what is that? 2.1. And there you go. Well, wow, you have 490, but don't just directly write down 490. This is, after all, 3 marks, and this is a show that question. My advice is, because I've been a victim of this, always in any show that questions, make sure you show each and every single step. Okay? If you don't, I promise you it's gonna suck. You're gonna lose like 1 mark, and you're gonna get like 74, and you're gonna find out that, oh shit, that was a show that question, and I just felt lazy and I didn't show that 1 step. No, bro, come on, don't do that. So what I'm gonna do here is write down 350 times 2.1 divided by 1.5. That's gonna be equal to 350 times 2.1 divided by 1.5. Yup, we do get 490. Thank God. 490 newtons. There we go. And then finally, you can actually just write down shown in brackets. I don't know if this carries any marks. I think you could just write down 490 newtons. That's it. But yeah, the paranoia gets students. Okay, a particle P of weight 210 newtons attached to the rod at distance d meters from A. Okay, d meters from A. Let's just erase these. Okay. Let's just erase that. And that. And that. Just cleaning things up. A particle is attached to the rod. Oh god, I just had dinner and oh god, I'm feeling weird. Okay, d meters from A. The tension in the rope at C is now 600 newtons. Alright. Okay. The rod remains in equilibrium. Still in equilibrium though. Now we don't actually know if the particle is like here or here. So let's just assume that it's here. And then once we find out the distance and find that the distance is actually less than 2.1, meaning that would just imply that the particle is actually here. We don't know that, so we're just going to assume that it's right here. It's acting through this point, through this line. That's going to be 210 newtons. And the whole thing is just distance d, okay? And the tension in the rope at C now is 600, so we can actually just erase that and say that this is 600 newtons. Also, in the exam, of course, you're not just going to have a tablet right here and erase as you want. So what I suggest you do is just draw the whole beam again, okay? That is what you have to do, just to avoid any silly mistakes. Please do that. All right, now the tension in the rod, we already took care of that. Find the value of D. Okay, we just want to find the value of D, and the rod still remains in equilibrium. How can we do that? I'm just gonna do this here, okay? All right, so for B, we have to find out, do we have, oh, we already know W. This is 490. Why don't we write that down? Exactly. Now we can simply just take moments about A, because if you even think of taking moments about C, well, the first problem is that we don't have TA. But yes, then you could say that you could just find out TA by resolving vertically, because you know weight now and you know this 210 as well, so the downward forces, they're just going to be equal to the upward forces, and then you can solve for TA. Yes, you find that, that's all right, but the problem with that is, you know how I said that we don't actually know where this particle P is? It could either be here or here. So when you take moments about C, you're just going to be confused about whether to take the clockwise moment or the anti-clockwise moment. You know what I mean? It would just not work, okay? Maybe it would work only if you get lucky, okay? But you should probably try it out sometime, and you're just going to find that you're going to get two different answers. I don't know. I've never tried that, but yeah, the fact of the matter is, just don't do that. It's just best if you just take moments about A, because that way you know that, well, P is, it doesn't matter if P is here or here, this is always going to cause a clockwise moment. I just keep forgetting which is clockwise and anti-clockwise. It just has to go to my head. All right. Here, yeah, okay, I was going to do this here. So moments about A, we just write this down like that, M and then bracket A, is going to be, well, first of all, let's take care of the clockwise moments. 490 multiplied by 1.5 plus 240 multiplied by, that is going to be D. That is going to be equal to the total anti-clockwise moment. The anti-clockwise moment is 600 times 2.1. 600 times 2.1. There we go. Now we just solve for D. That's simple. That's what we have to find out. And again, even though it's not a show that question, why don't you just write the next step, right? Just write this down and then put this into the calculator. Don't just, I don't know, put this entire first line in the calculator. I don't know how you do that even. Okay, 600 times 2.1 minus 490 times 1.5 divided by 240. That's what we're concerned of. And we get 600 times 2.1 minus 490 times 1.5 divided by 240. There we go. 35 over 16. 35 over 16, that's just going to be, let's use the approximate sign here. That's going to be 2.19 meters. So we can actually see that this is greater than 2.1 meters. So now we have just confirmed that particle P is actually like beyond C, toward the right of C. Particle P is removed from the rock, and now we're just done with particle P. This is just gone. So why don't we just erase it from here? Just to avoid any confusion. Again, in your exam paper, you can't just erase it like that. Oh, actually, oh, I'm so dumb. Well, if you could just draw the diagram with a pencil, right? And then erase it when you need it. Because they're not going to mark you for drawing or labeling diagrams, right? So yeah, you could actually do that. I'm so dumb. Alright. Okay, we just erased that. What else do we need? Okay, since there is no particle P anymore, this tension is not going to be 600 anymore. It's going to be different. Particle P is removed. Particle Q of weight X Newton is now attached at B. Okay, now we just have X Newtons attached at B. Oh, by the way, you see how we say that the weight is acting here and the weight is causing a moment? You know how we say that? Like for here, this particle Q is gonna create a moment with its X newtons of force. That's not exactly the right way to describe that. It has the same analogy of this, the tension being the reaction force, whatnot. So here, what's actually going on is there's a particle just standing right here, just still, right over here. there is a contact between the particle and the beam. That would mean there's a reaction force between them. What's the reaction force going to be? Well, we just know that the particle Q has a weight of x, all right? And we can see that the particle is in equilibrium, meaning it's not moving, meaning it has resultant force of 0, meaning that there must be some upward force to balance that, right? To make the resultant force 0. And that force is the reaction force exerted by the beam. That is also going to be x in this case. It has to be equal to the weight, of course. This reaction force is exerted by the beam, right? Now, due to Newton's third law, the particle is now going to exert the same force on the beam, but just downwards. And that is also going to be equal to x. And this x is really what we're concerned about. Like, you know how we, for particle P, we said weight 210 newtons? There is a particle P, and we said weight 210 newtons. The weight is not exactly the force that is creating the moment. It's actually the reaction force acting on the beam. We're really concerned about the beam, the moments, or the forces on the beam that's creating the moments and stuff. That is what we're interested in, not just the weight. So how we say that the weight is contributing to the moment, it's not exactly the right. But yeah, I mean, sure, this... it's not a big deal, but I just thought you should know this as well. So yeah, there's that. You don't have to think much of this, honestly. I just yap a lot. I just want you to understand, really. I just don't want you to just follow anyone blindly, okay? So you have x newtons right there. Now, how do we find this out? It still says that the rod remains in equilibrium and is now on the point of tilting. Oh, okay. Now it's on the point of tilting. So when particle P was there, it was not tilting, it was just resting at equilibrium. Now it's actually on the point of tilting. Now, how do we figure out in which direction is it going to tilt? Well, it's just common sense. You have, like, let's say before attaching any particle at B, this was just at equilibrium. Okay, and then you just add a weight over here, and that weight is x newton, and then that's the reaction force of x newton here on the beam. And, well, this is the particle Q, of course. Okay, and then, of course, it's going to create a force on the beam here. Therefore, it's going to try to create a moment in this direction. So you know that it's going to try to tilt this way if it does tilt. But it just says in the question is about to tilt. So it does indeed tilt, but okay, no, it does not tilt. It's just on the verge of tilting. Like, if you go like Q plus some extra force, you add like 0.1 newton of force, 0.001, it's just going to tilt. That's what's happening. It's just at equilibrium. So what happens when you actually tilt? So this part is trying to go this way in this direction, and this part is trying to go up. So that is how the beam is going to try to rotate. Okay, now notice what happens to the string at A. Extremely sorry. As the beam is on the verge of tilting, the beam is going to try to move up. At this end, of course, not up at B, that's going to be down, of course, it's rotating. So here, it's trying to go up. So when it actually goes a little up, you just move just like a very small distance, a virtually negligible distance, but it's just enough to make sure that the tension at A is 0. And how does the tension become 0? Well, the movement is like very slight, but it is actually causing the string to go slack. Okay, you're gonna push up on a string here. You can't expect the string to be still be taut. It's going to be slacking, right? Just like you're doing right now. Okay. Sorry. Okay, so when the string goes slack like this, the tension is just going to be 0. So that's actually very important information here, because since we know that the tension there is 0, what we can say, or what we can do rather, is take moments about C. Okay, if we take moments about C, we don't really have to think about what the tension here is, right? Or even what the tension at C is. because we're taking moments about C. So we're not even concerned about the moment that is created by this force, and there is no moment created because, well, the distance of this force, this tension right here from the pivot is just zero. The perpendicular distance, right, is just zero, is acting through the pivot, so of course it's not going to create any moment. So we're not really concerned about the tensions, which is why it's really beneficial that the string goes slack at A. So now we can just take moments about C, and well, we have x multiplied by, this is going to be the clockwise moment first, x multiplied. Also, if you're wondering, like, you don't actually have to write down the clockwise moments first and then equate it to anti-clockwise moment. You can just do the opposite as well. Just saying. I'm sure you know that. I'm just saying for anyone wondering. So you have x multiplied by, what is this distance? This distance is going to be 3 minus 2.1, that is 0.9. So like 0.9, there we go. That is equal to 490 times, what is this distance? Okay, so like the whole thing is 2.1, this is 1.5, so 2.1 minus 1.5 is 0.6. There we go. And x is just equal to 490 times 0.6 divided by 0.9. That's just 980 by 3. And again, you could probably keep it like that, but I just like to do this. 327 Newton. That is, I think that's fine, but you could keep it as 980 by 3 as well. Both will score you marks. Now, okay.